Last time I said P was the class of problems, and they're decision problems, yes-no problems, such that there exists an algorithm that solves that problem, which is always correct, it's deterministic, and its worst-case running time is bounded by some polynomial function of the input size. Okay, so this was the definition in terms of problems. And then informally, this NP was, there are decision problems where a polytime checker exists. But actually, neither of these definitions that we did last time and examples we did last time are formally correct. And so that's what I want to do today is to really make this formally correct. So first of all, even P has to be modified because the formal way that this whole theory of NP and NP completeness was developed was in terms of sets, and which are also called languages. And instead, these are yes-no problems. And so we think of the set of instances. So we have a problem. We think of the set of instances where the answer to the problem is yes. Okay? So given problem, say y, well, okay, problem, we've been talking about problem y, such as, say, vertex cover. Okay, so we have this problem, the general problem vertex cover. And what are the instances of vertex cover? It's a graph along with a target. Okay, so an instance of vertex cover is a graph and then some particular number, which is a target. And the question is there a vertex cover of that size or smaller? All right, so input or instance is a graph, G, and a target, call it K. Okay, and so an input, so Y denotes an input or an instance to the problem. And then we can talk about Y contained in capital Y. Okay, what does this mean? If Y is contained in capital Y, or in this case, Y is, or the input, the graph and the target is contained in vertex cover. So you think of this as not just the name of a problem, but to identify a set of instances, and Y identifies a set of instances. And one of those instances, these are the instances where the answer to the vertex cover problem is yes. Okay? So if and only if the answer to problem, in this case, vertex cover, but in general, it's Y, call it Y, is yes. Okay. Last lecture I told you that today's lecture is going to be weird and formal because that's the way this whole theory has sort of developed in a technically weird sense. And this is the first part of it that is, in my opinion, just unnecessarily ornate and weird. But that's what's, the book follows that tradition, and so if I'm going to make the book make sense, I have to explain all this stuff. So instead of talking about, oh, we've got this problem, we have input, and the answer is either yes or no, we talk about, here's this set. And an instance is in the set if and only if the answer to the problem is yes. So we just added a layer of clutter, conceptual clutter on top of it. We did nothing of any importance, but there it is, and the book is written that way, so it won't make sense unless we do that. So we're not talking about problems anymore. We're talking about sets and languages. Okay? Everybody get that? You have to be a mathematician to love this, this level of additional abstraction where you just make things more difficult. Okay. Actually, there's a really technical point why this is valuable to look at this way. So P is the set of languages. Now we don't think of problems anymore. It's the set of languages where there is a polynomial time algorithm that correctly decides if an arbitrary instance languages called, well, where there's an arbitrary instance is in the language. Okay, so let me write that another way. A problem P, a problem Y is in P. Let me make this a little scripted. Y is contained in P if and only if there is a polytime algorithm to decide, that means yes or no, if any input little y is contained in capital Y. All right? So again, we just, in an ornate way, just said that capital P, the script P, is the set of all problems, if you want to think about problems, where there exists a polynomial time algorithm that can solve the problem, and it's a decision problem, so it gives yes or no. But now we've translated this into this language of languages. So P is the set of languages where blah, blah, blah. Okay? So how many people here have taken CS 120? Okay, so those of you are probably more comfortable with this whole notion of languages and deciding whether an input is in the language. So all of this theory of NP completeness comes out of that tradition, and that's why it's cast this way. Okay. Have we done anything yet? Anything with any real substance, or this is all just definitional? It's all just words at this point. We have P. But we do have examples of languages that are in P. Okay? What's an example of a language that's in P that we've seen in this class? Nobody? What? Okay, shortest path, if we turn it into a decision question, if we said, here's a graph and here's a target, is there a shortest path that's less than or equal to that length? Yes, that definitely so, because we've seen polynomial time algorithms for that problem, and that's in P. What's an example of a problem that we didn't claim was in P in this class? Any problem we've seen where the only algorithms we have for that are exponential time? Well, last time yeah. Vertex cover. Yeah, the only algorithms we have for vertex cover, in comes the graph and a target, and we want to know if there's a vertex cover of that size or less, and the only algorithms we have really just enumerated subsets of that size and asked whether there was a vertex cover of that size. And then you would enumerate and look at each one of those subsets, and that's exponential time. Okay, so we have problems that are known to be in P, and we have problems we've looked at that are not known to be in P. Last time I mentioned not knowing to be in P is different than knowing not to be in P. Okay, so that's a subtle difference, and you need to pay attention to that one. Okay, so we've got P. Now, NP Last time I said informally that was the set of problems such that there exists a polynomial time algorithm that can take in a proposed solution and check if that proposed solution is correct or not. And we saw some examples of that. For example, a vertex cover is an NP. If the instance of the problem, vertex cover problem, is a graph and a target, and you have a proposed solution which is some subset of vertices, some set of nodes, an algorithm can certainly look at those nodes, look at the graph, look at the target, and figure out whether that subset of nodes is in fact a vertex cover and is its size within the target range. Okay? And that kind of checking is a very simple polynomial time algorithm. So vertex cover, under that informal definition, is an NP. But it turns out that informal definition is not what we actually use, and it's not just to make life more difficult. So here's the first case where the technical requirement, the pure technical definition really has some meaning. It'll allow us to prove something that otherwise we couldn't. So I want to define, in order to get to NP, I want to define B, that's an algorithm, is an efficient certifier for problem Y. So Y is again a problem. You can think of it as vertex cover if you like, or whatever problem you like. It's a decision question, decision problem, yes or no answer. If B takes in instance S, so S, well, let me, now I'm deviating, I guess, from the book, but I'll be a little closer to what I've put up here. So we'll call little y as an instance, okay? So B takes in an instance of that problem, of that an instance of that problem or language, and it has to decide. If we're looking for the decision version, an algorithm that decides it, it would want to know whether little y is in capital Y. But a certifier doesn't answer that question. What a certifier does is this: it takes in the instance, and it takes in a string, call it little t. Now, that string t is sometimes called a hint. It's sometimes called a certificate. Sometimes it's called a proof. What else do we call it sometimes? Hint, certificate, proof. There's some other names that are given to it. But it plays the role of the proposed solution. So in the informal version of this that we did last time, in comes to the certifier, an instance of the problem comes in and a proposed solution. But here we're just vague about what it is. It's just a string, okay? And it's called these various things. So I guess I could sometimes call it a proposed solution, but that's actually the least informative word for this, okay? So okay, so we're still defining what it means to be an efficient certifier. So what we know is what comes into it. Here's B, income, and this is B for problem Y. Okay, so in comes instances of problem Y, and also this extra information, this extra string. And then what we require of B are several things. One is B runs in polynomial time, what, as a function of the length of the input, y, and t. I'll just write it that way. So this is the length of the input. Input is y and also t. Now actually, okay, well, I may change that in a minute. And 2, there is a polynomial function p. This is little p. Now let's call it f. Too many f such that little y is in capital Y, if and only if there exists a t where t is less than or equal to f of y, and byt equals yes. Now, I told you last lecture was the intuitive one, and that would make a lot more sense to the 13 of you who are here than this technical definition. This is all the book gives you. It doesn't give the intuitive one. So what is this doing? This is just, I mean, even I have to just have a crib sheet. I couldn't do this from memory. And right, I couldn't do it correctly. Okay, first of all, byt. This is the output of this algorithm B. Okay? So the algorithm B can do several things. It can output yes, it can output no, and it can just spin its wheels, not output anything. Okay? So this is this is saying that the algorithm B, when it's given input y and it's given this string t, it says yes. All right? So we know it does it in polynomial time. That's what the first thing says. This algorithm B runs in polynomial time. And the size of t that it's given is bounded by a polynomial function of the size of the input, y. Okay? So t isn't very big in comparison to the size of y. Right, so y is your, like the graph for vertex cover, and t is your additional hint or piece of information. And we don't want the size of y to be more than polynomial as a function of the size of y. Okay? So we have that. And this is saying that little y will be in capital Y if and only if there is this hint such that it's small, relatively small, and this algorithm, when it looks at the input y and it looks at t, it says yes. And that's what it means to be an efficient certifier for a problem y. So you can feed it instances, and you can feed it these additional hints which have this property, okay? And then it will say yes, but only if it really, only if y, little y is contained in capital Y. All right? It should never say yes if, in fact, little y is not in capital Y. Okay? All right. I don't know how to. Well, I'll try to make this a little more concrete, where I make, instead of B, we say vertex cover. Okay, so this is going to be a certifier for instead of Y, we're saying vertex cover. Okay? And what is the input to the certifier? Well, it's some particular graph G. Graph G, and a target K. All right, that's what the input, that's what input to the vertex cover problem looks like. So this is essentially, we're saying little y is equal to the graph and the target. Okay? And we want this algorithm, we want this algorithm to be an efficient certifier for vertex cover. So to be an efficient certifier, first of all, it has to run in polynomial time as a function of the input y, and also in the input t, which we haven't yet decided on what it's going to be, but there's going to be this additional input t. And there has to be some polynomial function f such that the strings t that you give this are not huge. They're bounded by a polynomial function of the size of little y. Yeah?
For number 1, is that supposed to be the absolute value of y times t, or is it just y comma t?
I just said I was abusing notation here, where I'm saying this is a polynomial function of both of them. Okay, so, yeah, okay, I guess it could have been more if I did that. Okay. That would be okay. Now, some definitions just say it should be a polynomial function of y, and then they have this additional thing, and then it then follows that it runs in a polynomial time of both of these. But I'm trying to be a little more explicit. That's just an extra little level of conceptual difficulty that mathematicians love. You know, why say two clear things when you can say one unclear thing? All right. So I'm being very explicit here to add both of these in here. And I'm not sure which way the book does it. Yeah?
How does the function f relate to b?
F is a polynomial function on the length of y, and we're just saying that the hint can't be big in that sense with respect to the input y. So there has to be some polynomial function on the input size y which bounds the input size t. So it doesn't directly relate to b in that sense.
So it can be any arbitrary polynomial time function?
A polynomial function is a function of size now, not time. Yes, but there has to be one. Okay, so there has to exist some polynomial function, f. So there's a polynomial function f such that the instance y is actually in capital Y. So what does this mean? So gk is contained in vertex cover. Okay. If and only if the algorithm b on input y and t gives yes. Okay. And the certificate, the hint, is its size is bounded by a polynomial of the size of y. So what should t be in this very specific case of vertex cover? What should t be? We talked about vertex cover last time in specific, in sort of the informal sense. What was the, and I mentioned it today, what was the proposed solution in the case of vertex cover? Yeah. It was a subset of vertices. Okay? So here, in this formality, we can have T is equal to subset of vertices that form a vertex cover of G of size less than, or actually I've been saying it, size equal to K. Okay? So if this is specifically what we're going to do for vertex cover, does it satisfy this definition? And what is B? B is going to be an algorithm that looks at the graph, looks at the target, looks at the subset of vertices, and just checks, is that a vertex cover? Which you can do in a very direct, simple algorithm. Is its size equal to k? All right, and which again is a simple check. And so B certainly runs in polynomial time as a function of the input and the function of the size of the hint. Okay? Because all that B is going to be doing is look at this hint. It's a subset of vertices. Check whether it's a vertex cover. That means is every edge adjacent to one of the nodes that's in this little set T, and is the size of T equal to K. So those are all very simple checks, clearly polynomial time. So B runs in polynomial time as a function of its given input. F, we need to see that the size of the input T is always bounded by some polynomial of the size of the input. Okay? Well, what's the input? It's a graph and additional information. And what's T? It's a subset of nodes. So T is, in fact, smaller than G. All right? And so no matter what G is, however big it is or small it is, the T that we're going to give under this particular scheme, is it size bounded by a polynomial of the size of the input? Well, yes, it is, because it's in fact always smaller. So the simple polynomial here is, in fact, linear. Okay? So that's satisfied. And Y is in capital Y. That is, there really is a vertex cover of size K if and only if this particular algorithm, this particular checker that I've just specified, says yes. Okay? Well, so you have to think about it in both directions. If what you give the checker, if what you give the certifier is a graph that really does have a vertex cover of size K, and you give it a T which is in fact a vertex cover of size K, then that checker is going to say yes, because all the checker is doing is looking at the proposed input. On the other hand, this is the subtle part that people usually forget when you first learn about this. Suppose that Y is not in, the input is not in capital Y. That is, you're given a graph, the input is a graph in a target K where there is no vertex cover of size K. All right? Can you think of a hint T that's going to confuse this particular checker, which after all is just going to look at the vertices, is intended to take in T as a set of vertices and look at those and see whether or not that's a vertex cover of the appropriate size? Can you think of some string that you can give that checker which is going to confuse it to say yes, even though the graph and the target do not form a vertex cover of that size? Okay? And remember, this checker, all it's doing is saying, I think that T is a set of nodes. I'm going to interpret those as a set of nodes and look to see whether that's a vertex cover in the given graph and whether it's the appropriate size. If you give it some garbage in T and it can't interpret it as a set of nodes, it's not going to say yes. I'm going to build that into my B. Okay? It's only going to say yes when what it sees looks like a set of nodes and it has, those are actually vertex cover and it's the appropriate size. Then it's going to say yes. That's what my B will do. And therefore, I claim that you can't confuse it. You can't give it some garbage. Let's say you give it a subset of nodes that is not a vertex cover of size K. It'll interpret it as a subset of nodes because it has the right format, but it'll realize it's not a subset, it's not a vertex cover of size K, and it won't say yes. And if you just give it some garbage, it'll also not say yes. All right. So what I'm illustrating here is that for the problem vertex cover, there is a certifier, an efficient certifier. Okay? And this is what an efficient certifier means. Any questions on that? This is just technical, it's weird, but if you think about it for a while, it'll still be technical and weird. But you'll convince yourself that it does make some sense. Okay. And I said last time that 99.9, many, many infinite nines, of the problems that you'll ever see, and all the problems that we'll see in this class, for all the problems that we'll see in this class, you don't really need this technical definition. T, in that case, will really be a proposed solution. It will look like the, it'll be sensible and natural in terms of proposed solution, and therefore our informal definition would have been adequate. But there are problems where that informal definition is not adequate, and we need this formal technical one. And the example that I gave you last time was primality. So primality is the problem. You're given a number, an integer, and you want to know whether it's prime. Okay? So you can think of the language as the set of numbers, set of prime numbers. Okay? The decision question is you're given that number, is it prime? If there's an algorithm that can take in that number and run in polynomial time as a size of its, as a function of its input size, and now you'd have to talk about the number of bits in that number. Otherwise, you just say the input size is 1. But no, we want to say what's the actual size of the number of bits. If there's an algorithm that can do that and run in polynomial time, then primality is in capital P. All right? But to say that there's an efficient checker or efficient certifier, it means there has to be an algorithm B that runs in polynomial time and can take in the number, which is y, the number where we want to know whether it's prime or not, and some hint, where the hint can't be very big. Okay? Now, you could think of a number, inputting a number, I don't know, 20158672, and a hint. What's a hint to show that it's prime? What's a good hint to show that it's prime? Yeah. Even numbers, I think.
You're checking if it's even or not, and that fails the number.
All primes are odd, aren't they? Except for 2. So yeah, but among the odd numbers, there are many that are prime and most that are not prime, right? So what's a hint? If this is a number that comes in, what's a hint when this is actually a prime number? What's a hint that's not too big that will convince a polynomial time algorithm that this is a prime number? Yeah. The what?
Prime factorization.
The factorization, but a prime number means there is no factorization. It's just 1 times itself.
So if you had prime factorization and you knew that both those numbers were prime and it's just 1 in that number, then, or just that number itself, then you would know it's prime.
Well, yeah, again, to be prime, it means that the number is equal just to itself times 1. Okay? And there's no further factorization of that. Okay? So here, that hint would be nothing more than the number itself. Or it would be nothing more than the word yes, it is prime. But what could that algorithm be that's going to take in the number and a word yes and never get confused? Okay, you could, if it looks at, oh, this says yes, I'll say yes. Well, definitely you could fool it. Remember, this says the number is prime if and only if the algorithm B says yes. So if all the algorithm B is doing is looking at the word yes, or you're saying the prime factorization is just the number times itself, well, I can fool it and give it the number 15, which is not prime. Here's 15, here's the word yes, and then B will say yes, and it wouldn't be doing the right thing. So I don't expect anybody to actually know what a hint is, but in fact there is a polynomial-sized hint that you can always give in the case of the primality, so that a polynomial time algorithm checker, certifier, actually does the right thing. That when this number is really prime, there is a short, it's also sometimes called a proof, a short proof of that, which will make this polynomial time algorithm say yes, but it'll only say yes when in fact this number is prime. So, but what T is in this case follows this definition. It's a string. It's not a proposed solution, because a proposed solution in this case is just the word yes or no. And how can the word yes or no be helpful to an algorithm that's in polynomial time trying to check whether it's prime if we don't also have an algorithm that in polynomial time can just take in the number and determine if it's prime or not. I don't actually know I've forgotten. I've not paid attention. There's been some progress in primality checking, whether primality checking is in P or not. Does anybody know? Well, at any rate, this is an example where it's in NP, was known to be an NP through the fact that there is a small proof, even when it was not known whether or not it was in P. Okay, I warned everybody this was going to be a technical and weird lecture. Anybody disagree with me yet so far? Okay, so this is technical and weird. We've seen an example. Let's get on to NP. NP is the set of all languages where for any language in NP, any language Y in NP, there is an efficient certifier for Y. Okay. So it's the set of languages where, yes, for each one of them, there's an efficient certifier. For each one of them, so back to the informal way of talking about it, NP is the set of all problems such that there's a polynomial time algorithm. For each problem in NP, there's a polynomial time algorithm for taking in a proposed solution and deciding whether that is a real solution or not. That's the informal definition that works for every problem we're going to see, and almost every problem that anybody has ever focused on and shown to be an NP. That informal definition works. But for some problems, for example, primality, that definition does not work, and that's one of the reasons we needed this more grotesque definition. Okay? So now we can actually prove a theorem, which we could not prove with the informal definition. Theorem, capital P is contained in NP. So the set, capital P, the set of all those languages that are in capital P is contained in the set of all those languages that are in NP. That we can actually prove. Okay? So how do we prove that? This is like a one-line proof if you understand the definitions. So again, to be in P, that's, let's say, a language Y. A language Y is in P if and only if there is a polynomial time algorithm that can take in any instance, little y, and decide correctly if little y is in capital Y. Decide correctly means it gives out an answer yes or no. Okay? So this is what it means to be in capital P. What it means to be in NP is that there's a polynomial time algorithm which can take in an instance y and a hint t, which is not huge, and it runs in polynomial time. And if, in fact, y is in capital Y, it'll say yes. And only if y is in capital Y will it say yes. Otherwise, it'll either say no or it might spin its wheels and say nothing. But it's only going to say yes when it should, if and only if little y is in capital Y. So if we take a problem y, which is in capital P, how do we prove that it's in NP? Michael.
You could say that B is the polynomial time algorithm to solve y, and then just ignore t.
Right. Okay, so if and only if there is a polynomial time algorithm, and let's call it capital A. Okay, so now we want to see that there's in fact a checker for a polynomial. There's an efficient certifier for that problem y. So what are we going to make it look like? What is it going to be? Well, it's going to be A sitting inside here. Okay, so this is what B actually looks like. Inside of it is a copy of A. And it takes in little y, and it takes in whatever the hint is. And what it does is it ignores the hint. Okay, then it does its computation on y, and out comes yes. And in fact, if it's about to say no, it could say no, or we could even cut that off. So this A is polynomial time. It just looks in the input y. If it decides that y is in capital Y, it'll say yes. If it decides that y is not in capital Y, and it will decide one or the other because capital A is a decider. It's an algorithm that can actually say yes or no. Okay? If it says no, if it decides no, it could, to be courteous, it could output no, but it doesn't have to even in terms of the definition. As long as it outputs yes, if and only if y is in capital Y, then this is a setup which proves that that language y is in capital P. So when you're in capital P, that's a really strong statement. So it almost trivially follows that you're in NP by this argument. Now, if you think back to the informal definition, where P was the set of all problems that could be solved in polynomial time, and NP was the set of all problems that could be checked in polynomial time, you couldn't prove this because the definitions just don't mesh properly. The mere fact that the problem can be solved in polynomial time, how does that tell you that that a proposed solution can be checked in polynomial time? You're back to this issue of, for example, primality checking. So this theorem couldn't be proven with the wrong definition, with the informal definitions, but it's trivial with the right definitions. Okay, so that's one fact. That's a trivial fact. Now I want to define NP completeness. We have 1 minute, and that's all we need. Definition, a language Y is NP complete. NP complete if 1, y is in NP, okay? So it has to be an NP. That's a rather trivial thing. And 2, for any language X that's also an NP, X reduces in polynomial time to Y. Okay? So remember what polynomial time reduction is, that we did that last time. Heavy emphasis on, and maybe even the lecture before that. But, look at the videos. Polynomial time reduction. So a language is NP, Y is NP complete if, well, first of all, this. But any other language that happens to be an NP, you can reduce it in polynomial time to Y. Okay? So I'll end with that definition, and next time we'll exploit this to get some immediate theorems that tell you why NP and NP completeness are important.